All right, everyone. Welcome to the last part of this lecture. Again, we started with a parallel RLC circuit and the natural response. We looked at sorry, we looked at its natural response of a parallel RLC circuit. When we solved the circuit, we ended up figuring out it's a second order differential equation. We assumed the solution, came up with a characteristic equation, find the roots. And then we also looked at the Napier and the resonant frequencies, resonant radiant frequency, omega naught. We looked at how the alpha and omega naught are compared to each other. We can have three possible solutions: overdamped, underdamped, and critically damped. And we were looking at overdamped natural response. And we came up with literally the summary of the entire thing that we talked about. And if you know this slide, you can do most of the circuit problems. Other than the derivations for that, you need to understand the concepts. Okay, if we were to solve any parallel RLC circuit, overdamped natural response circuits, this is what we really need to do. Solve the circuit for t is less than 0 and find out the values of the initial capacitor voltage and initial inductor current, I naught and V naught, if they are not given in the question. Once you ended up finding these things out, you have to solve for the alpha and omega naught. Alpha and omega naught over here, all you need to do is the values of the resistor, capacitor, and inductor, right? So once you find alpha and omega naught, you prove that which response it is. Since we are talking about overtime, so your alpha must be greater than omega naught square. Alpha squared must be greater than omega naught square. And this equation should be valid. This equation represents the voltage solution. In order to get this equation exactly figured out, we need to have the values of A1, A2, and S1 and S2. And just by knowing the values of alpha and omega that we have already found, we can figure out the values of S1 and S2, right? Here's the equation. And once we figure out the values of S1 and S2, we need to find the values of A1 and A2, right? We did the whole derivation of how to figure out these two values. Essentially, this represents the value of the at 0, and the second equation represents the value at the first derivative at 0. So this is the other kind of a initial condition of the constant. So this is based on these two equations. You can figure out the values of A1 and A2 as well. You can solve for that because we know the rest of the variables. And once you knew that, you can put them back over here on the original second order differential equation, right? And literally know everything. You can easily figure out at least a voltage. And then based on the circuit, all you need to do is to compute the currents that we have seen in the past, how to do that. And we're going to do an example problem as well. Again, maybe all you need to do is to remember the right hand side of this slide, just to make your life even more easier. Okay, so let's get started and see. Today we're going to do a couple of example problems based on the overdamped natural response. Okay, so here's the circuit. Again, this is a parallel RLC circuit. I can see my resistance, my inductance, my capacitance. This is exactly the circuit that we have been trying to derive an equations for. And interestingly, just to make our lives easier, the problem provides us the values of the initial conditions, right? So your initial value, initial condition, the voltage, across the capacitor is 12 volts, and the inductor current is 30 milliamperes. Okay. And it asks you to find the expression for Vt, right? So in A, we need to find what is the value of Vt. We looked at what is the value of Vt over here. What is the expression for the Vt? Vt expression is over here, right? So essentially, we need to find A1, A2, S1, S2, and I'm going to write the equation now, right? So let me maybe write the equation over here again. So it was A1, S1, e raised to power S1t. Let me see. No, sorry, there was no S1. There's A1 e raised to power S1t plus A2 e raised to power S2t. So I need to find the values of A1, A2, S1, and S2. Anyhow, I already knew my initial conditions. When I know my initial condition, the other thing to do would be find the values of your Napier frequency, omega naught, and your resonant radiant frequency, omega naught, and Napier frequency, alpha. Okay, so your alpha is 1 over 2 times RC, 1 over 2, R is 200 ohms, and C is 0.2 microfarad. I guess this is piggybacking on the previous example problem that we did. So your alpha comes out to be 12,500 radian per second. Let's find the value of omega naught as well. The value of the omega naught is 1 over LC, or you can find the value of omega naught square. Omega naught square is 1 over LC, so 1 over inductor is 50 millihenry. So you get 50 times 10 to the minus 3, C 0.2 microfarad. Omega naught squared come out to be 10 to the 8 radian per second squared. Radian squared per second squared. Okay. Now we can see that since my omega naught square is less than alpha square, once I'm going to find the S1 and S2, I'm also going to realize that both of them are going to come out to be real and distinct, right? But omega naught squared less than alpha square means that response is overdamped. And if the response is overdamped, I can use this equation. If I can use this equation, let's find the roots, S1 and S2, and then A1 and A2. Right? S1 and 2 is, if you remember from the equation, it was minus alpha plus minus alpha square minus omega naught square. Right? So I'm just going to replace the values. Minus alpha is minus 12,500 plus alpha square is 12,500 square minus omega naught square is 10 to the 8. S1 is going to come out to be minus 5,000 radian per second. And similarly, I'm going to do S2, which is going to be minus alpha square minus omega naught square. And once you're going to replace the values, it's going to come out to be minus 20,000 radian per second. So I ended up finding the values of both S1 and S2. And I am left with what? In this equation, I just need to find the values of A1 and A2 now. Okay, and in order to find the values of A1 and A2, I had two equations, if you remember, right? One of my equations is A1 plus A2 equals V naught. V naught is 12 volts. So this is equation number 1. The other equation was, if you remember, A1S1 plus A2S2 equals 1 over C minus V naught over R minus I naught equals, okay. What is the value of the I naught? I naught value is 30 milliamperes. The value of the V naught is 12 volts. The value of the resistance is 200 ohms. The value of the capacitance is 0.2 microfarad. S1 is minus 5,000. S2 is minus 20,000. So I got a second equation. Okay. Maybe I can write this down again. Right. So I got again A1 plus A2 equals 12. And then A1 S1 plus A2 S2 comes out to be 1 over C times minus V naught over R minus I naught. So forget about the right hand side. I'm going to come back to that in a second. Right, so A1, I need to find it. S1 is minus 5,000 radian per second plus A2, S2 is minus 20,000 radian per second equals 1 over C is 0.2 microfarad minus V naught is 12 divided by R is 200 ohms minus I naught is 30 milliamperes, 0.03. Okay, if I were to solve both of these equations, right, my value for the A1 is going to come out to be minus 14 volts, and the value of the A2 is going to come out to be 26 volts. Again, these are the constants of a second order differential equation where variable was a voltage. So that is why the units over here are the volts. So you should know the units, otherwise, yeah, your numbers will be cut off in exams too. Okay, so once you do that, once we ended up finding the values of the A1, A2, S1, and S2, all we are left with is to write down the equation. And the equation was, if you remember, Vt is A1 e raised to power S1t plus a2 e raised to power s2t, right? And again, this equation is valid for t greater than or equals to 0. So let's write down the equation. Vt equals a1 is minus 14, e s1 is minus 5000, t plus a2 is 26, s2 is minus 20k, minus 20,000, t, right? And this is t is greater or equals to 0. So this is the value of the voltage that comes out to be. Sorry, the second part is it asks you to sketch the value of the Vt for this interval 0 to 250 microseconds, right? So you can easily use any other MATLAB or any other, even Excel, to plot this thing. You can pick an array of time, different values, and have this kind of a plot. So in between 0 to 250 microsecond interval. So you can see that, by the way, right? This is not just decaying like this. This is going all the way down and then going up. And the interesting thing is that here, 12 volt, which is the initial value of the capacitor voltage. I'm not going to ask you to make these draws until I'm going to allow you the graphical calculators in the exams. But I may ask you to draw not scale version of how the response is going to look like without worrying about the exact values, other than the values that you should know. For example, you should know the initial value over here of the capacitor voltage, which was 12 volts, even given in the question, not even has to find it. All right, let's do the second part of this problem. The second part of this problem is we ended up finding, essentially this is just kind of an extension of this thing, right? We ended up finding the value of the Vt. And now the question asked, okay, so this is good. Find the value of the capacitor current, inductor current, and the resistor current. And we already kind of discussed that while we were making the derivations as well. Right? I can see that over here, my capacitor current is IC, and IC is C times dV by dt. So I'm just going to take I already know the value of this, right? I'm going to take a C times the derivative of this voltage that I have just calculated over here, right? So my current is going to be C times the derivative of this voltage, right? And then I have to find the value of the resistor current. Resistor current is the value of the V divided by R, right? So resistor current is going to be the value of the V divided by R. And how I can find the value of the inductor current over here, the parallel RLC circuit? Again, I can just apply a Kirchhoff's current law, and I would know that the summation of all the currents is equals to 0 here, right? So my inductor current should be equals to the capacitor current minus resistor current. So using these three equations, I can find the currents that are being asked in the next question. So it is asking, okay, find all of these values. Okay, so now let me solve that, right? So my first thing was the value of the voltage in that parallel RLC circuit. Essentially, I'm going to rewrite that equation. I'm going to rewrite this equation. E raised to power minus 5000t plus 26 e raised to power minus 20,000t. T is greater or equals to 0. Okay, so the first thing is that let's find the value of the resistor current. Maybe resistor current is a simple V over R. Resistor current IR of t, again IR of t is Vt divided by R, and R is just 200 ohms, so Vt divided by 200. Okay, so Vt divided by 200 ohms is again minus 14 divided by 200 plus 26 divided by 200, and again e raised to power minus 5000t e raised to power minus 20,000t. Right? I can express this in amperes or milliamperes. In case of a milliamperes, right, this is going to come out to be minus 70 e raised to power minus 5000t plus 130 e raised to power minus 20,000t milliamperes. So this is the value of the resistor current. Let's find the value of the capacitor current. the value of the capacitor current again is going to come out to be C dV by dt. So again, capacitor current is the value of the capacitor, which is practically speak 0.2 microfarad times the derivative of this voltage, right? If I were to take a derivative of this voltage, I'm gonna get minus 14 times minus 5,000, minus 14 times minus 5,000, e raised to power minus 5,000 minus 5,000 t, minus of 26 plus 26 times minus 20,000 times e raised to power minus 20,000 t. So capacitor current is going to come out to be again 0.2 microfarads. 14 times 5,000 is 70,000 e raised to power minus 5,000 t plus 26 times minus 20,000 is minus 520,000. So minus 520,000 e raised to power minus 20,000 t. And if once you're going to multiply with the with this thing to both of these, so your capacitor current is going to come out to be 14 times e raised to power minus 5,000 t minus 104 e raised to power minus 20,000 t milliampere. And again, if you remember, this should only be valid at z t is greater or equals to 0 positive, because there is no instantaneous change in the voltage, and the current is not going to change. So current is only valid at 0 positive, and the voltage doesn't change instantaneously in case of a capacitor. Okay, and then we find the resistor current, we find the capacitor current. The inductor current is essentially just a subtraction of the two, minus IR of t minus IC of t. So value of the inductor current is going to come out to be, you just need to subtract both of these things, right? Subtract both of these 5,000 minus 5,000 t terms and subtract the minus 20,000 t terms separately. So you're going to come out to be 56 e raised to power minus 5,000 t minus 26 e raised to power minus 20,000 t milliamperes. And here is your inductor current as well. Again, so this is pretty much the end of this short lecture as well, where we did a couple of other example problems, and we are pretty much done with the overdamped response. And in the next lecture, we're going to we're going to start to look at the underdamped response and the critically damped response, and also to do some of the example problems. Again, if I will summarize in a minute, we started with the natural response of a parallel RLC circuit. I ended up showing you the circuit. When we derived the equation, we came out to be this kind of a very interesting second order differential equation over here, right? And then we said that, okay, this is interesting. We are going to assume a solution A e raised to power st. Why? We discussed that in detail. Then we looked at how to find the, how did we get to this characteristic equation. And then it's a quadratic equation, so we ended up finding the two roots, S1 and S2. And based on those two roots, we ended up coming with these equations that based on the alpha and omega naught values, you can figure out the values of S1 and S2. And based on how the alpha and omega naught relates, you can have three different responses: overdamped, underdamped, and critically damped. Then we move forward with the overdamped response, and we looked at, in case of an overdamped response, we're going to have the real and distinct roots. So we can have these two solutions. Why we ended up going all the way over here is because we have a second order differential equation and we have two initial conditions, I naught and V naught. In order to find these initial conditions, we're going to have two constants, right? We can evaluate those two constants by at V naught and V dash of 0. And then we ended up solving all of this to came up with these two constants, these two equations, right? So one was this A1 plus A2 V naught, and the other one was this. After doing all of these derivations, we come up with this short really summary of everything. This is literally the summary of a parallel RLC response in an overdamped response systems. Parallel RLC circuit in an overdamped response. Um, and importantly, all you need to do maybe is to remember the right hand side over here. If you remember all of this, you don't need to remember anything else in order to solve the circuit, but you still understand the concept, please. Right? So you find the initial conditions, you find the alpha and omega naught values. From that, you figure it out S1 and S2. From that, you use these two equations to figure out A1 and A2, plug everything back into V of t, and then use the circuit, and then simply find the capacitor current, inductor current, and the resistor current. Okay, so with that, thank you so much. And the next lecture, we're going to start with the other responses. Thank you. Have a good rest of the day. Bye.